In September 2023, before the Euclid Space Telescope had even officially begun its science mission, an astronomer named Bruno Altieri was doing something routine. He was reviewing calibration images, deliberately out-of-focus test exposures taken to check the telescope's optical alignment, when something in one of those fuzzy frames caught his attention. There was a hint of something unusual around a galaxy that had been sitting in astronomy catalogs since the 1880s, a faint circular smear of light surrounding its nucleus. Altieri flagged it. The telescope was refocused. Better images were taken. And what came back stopped the team. Surrounding the center of the galaxy NGC 6505, a galaxy so close, cosmically speaking, that astronomers first cataloged it 140 years ago, was a perfect ring of light, an Einstein ring. One of the rarest and most beautiful phenomena in the observable universe, hiding in plain sight in one of the most studied regions of the sky, invisible to every telescope that had pointed at it for a century and a half, revealed in the first months of operation by an instrument that had not even finished its calibration phase. That accidental discovery in an out-of-focus test image was the first signal that the Euclid Space Telescope was going to spend its 6-year mission finding things that were always there, but that no instrument before it had been powerful enough or wide enough or precise enough to see. And in the 2 years since, nearly every major image Euclid has released has contained something that the scientific community did not expect. The Euclid Space Telescope was launched on July 1st, 2023, aboard a SpaceX Falcon 9 rocket from Cape Canaveral, Florida, on a mission that its builders describe as mapping the dark universe. Its target is not specific stars or galaxies or nebulae. Its target is the structure of the universe itself, the three-dimensional distribution of matter, dark matter, and the effects of dark energy across billions of light years of cosmic volume. To do this, Euclid is building a cosmic atlas. Over 6 years of operation, it will observe the shapes, positions, and distances of more than 1.5 billion galaxies across roughly 1/3 of the entire sky. From that atlas, scientists will extract 2 signatures. The first is weak gravitational lensing, the subtle distortion of galaxy shapes caused by the gravitational influence of dark matter halos between the galaxies and Earth. By measuring the statistical pattern of those distortions across billions of galaxy images, Euclid can reconstruct where dark matter is concentrated throughout the universe and how that concentration has evolved over cosmic time. The second is baryon acoustic oscillations, a specific scale of clustering in the galaxy distribution, imprinted by sound waves in the early universe, that serves as a standard ruler for measuring how the universe has expanded across its own history. Combining these 2 measurements across the full survey dataset will provide the most precise characterization of dark energy ever assembled, constraining whether it is a true cosmological constant or a dynamic field that changes over time. The Einstein ring discovery in NGC 6505 is the clearest demonstration of what Euclid's wide-field, high-resolution imaging capability can find that previous telescopes missed entirely. The galaxy NGC 6505 is a stone's throw away in cosmic terms, a mere 500 million light-years away, and astronomers first observed it in the 1880s. But this is the first time the ring of light surrounding its center has been detected, thanks to Euclid's high-resolution instruments. An Einstein ring forms through a phenomenon called gravitational lensing, when a massive object, a galaxy cluster, or a concentration of dark matter sits precisely between Earth and a more distant object. The mass of the foreground object warps the geometry of space around it. Light from the background object, instead of traveling in a straight line past the foreground mass, follows the curved geometry of space and is bent around the foreground object in multiple paths simultaneously. If the alignment is precise enough, if the background object, the foreground mass, and Earth are nearly perfectly aligned along the same line of sight, those multiple paths of bent light converge at Earth and form a complete ring around the foreground object. Professor Thomas Collett from the University of Portsmouth said, "Nearby lenses are exciting because they allow us to test the validity of general relativity on astronomical scales. The ring in NGC 6505 is formed by light from a galaxy 4.42 billion light-years away, bent around a galaxy 590 million light-years away. The background source is nearly 8 times farther away than the lens. Its light has been traveling toward Earth for 4.42 billion years, and only in the last 590 million years of that journey has it been bent by the mass of NGC 6505 into the ring that Euclid captured. The unexplained aspect of this discovery is not the ring itself. Gravitational lensing is well understood physics, but the fact that it was hiding in a galaxy that generations of astronomers examined without seeing it, revealed only by the combination of Euclid's wide-field survey and the attention of one scientist reviewing a blurry calibration image. On March 23, 2025, Euclid released an image that immediately broke records and generated more public attention than any single astronomical image in years. The target was the galactic bulge, the dense central region of the Milky Way, packed with hundreds of millions of stars and a volume of space that represents the oldest and most structurally complex part of our galaxy. This 6 gigapixel view of the galactic bulge is the largest high-resolution photo ever made of our Milky Way galaxy's center in visible light. The image was assembled from 9 separate exposures, each covering an area of sky larger than the full moon, taken over 26 hours. At 6 gigapixels, 6 billion pixels, it is so large that displaying it at full resolution on a standard computer monitor zoomed into the level of individual stars would require moving the view around for hours to see every region. One Euclid, which is hovering 930,000 miles from Earth, captured the image with its visible light camera over 26 hours in March 2025. What makes this image scientifically extraordinary is not just its size or its beauty. It is what the data contains. The galactic bulge is one of the densest stellar environments in the sky, so crowded with stars that individual objects are difficult to separate in conventional imaging. Euclid's optical resolution, combined with its sensitivity to faint magnitudes, resolves individual stars across this environment with a clarity that enables multiple simultaneous science programs from the same dataset. The new image from Euclid includes 51 known planetary systems and will assist in studying many more that will be found. Those planetary systems are detectable through a process called microlensing, the same gravitational bending physics that produces Einstein rings, but at a smaller scale. When one star drifts across the line of sight to another star, the foreground star's gravity briefly brightens the background star's light in a characteristic way. If the foreground star has a planet, that planet produces its own additional brightening spike in the light curve. By monitoring hundreds of millions of stars simultaneously across the galactic bulge with Euclid's survey cadence, scientists can detect these microlensing events and identify planetary companions to stars across enormous distances, finding planets that no transit or radial velocity survey could reach. The deep field images that Euclid released in March 2025, alongside the galactic bulge mosaic, revealed something in the distant universe that the scientific team described as a preview of what the full survey will show, and what it showed was already startling. The mission's first deep field data includes a preview of 3 cosmic areas that Euclid will observe for more than 40 weeks over the course of its prime mission, spotting faint and distant galaxies. One of those 3 deep field regions is called Deep Field South, and in the March 2025 release, Euclid published an image covering approximately 1.5% of the field, a fraction of what the full multi-year observation of that region will eventually produce. That 1.5% of one deep field contained a galaxy cluster located almost 6 billion light years away, surrounded by hundreds of background galaxies whose shapes were visibly distorted by the cluster's dark matter halo through weak gravitational lensing. The distortion pattern across those hundreds of galaxies is data. Specifically, it is a measurement of where dark matter is concentrated in that cluster and how massive that concentration is. Multiplied across 1.5 billion galaxies over the full 6-year survey, this kind of measurement becomes a complete map of dark matter across the observable universe, at a precision that no previous observatory could approach. The mission's first cosmology data will be released in October 2026. That October 2026 release will be the first time the full statistical power of Euclid's dark energy measurement, built from the combined weak lensing and baryon acoustic oscillation signal across the full survey dataset, is published. The scientific community has been building anticipation for that release for 3 years, since Euclid launched. What it contains may resolve or deepen the Hubble tension, the stubborn disagreement between different methods of measuring the universe's expansion rate that has defined the most important open problem in cosmology for the past decade. The unexplained images that Euclid has produced go beyond the Einstein ring and the galactic bulge. In 2024, the mission released an image of the galaxy cluster Abell 2390, located 2.7 billion light years from Earth, encompassing more than 50,000 galaxies. In the Abell 2390 image, the shapes of background galaxies, stretched and distorted by the cluster's dark matter halo, are visible to the naked eye as elongated arcs and smears of light arranged around the cluster's center. Direct visual evidence of dark matter sculpting the geometry of space in real time, frozen in a single photograph. In an earlier 2023 image of the Perseus galaxy cluster, Euclid revealed at least 1,000 gravitationally bound galaxies in the cluster foreground, with another 100,000 galaxies sprinkled across the more distant background, many of them never previously observed in any catalog. A single Euclid pointing produced more new galaxy detections than decades of targeted. Hubble observations of the same region could have accumulated. The difference is not that Euclid's mirror is larger. Hubble's is actually larger than Euclid's 1.2 meter primary. The difference is that Euclid's field of view is dramatically wider, covering areas of sky that Hubble's narrow field of view would require tens of thousands of separate pointings to image at comparable depth. By 2030, Euclid will create a cosmic map that covers almost a third of the sky, using a field of view far wider than NASA's Hubble and James Webb Space Telescopes, which are designed to study smaller areas in finer detail. The relationship between Euclid and JWST is explicitly complementary. Euclid casts the wide net that identifies the most interesting targets, and JWST provides the deep, high-resolution follow-up that characterizes them in detail. Mission planners with NASA's forthcoming Nancy Grace Roman Space Telescope will use Euclid's findings to inform Roman's complementary dark energy work. Scientists will use Roman, with its better sensitivity and sharpness, to extend the kind of science Euclid enables by studying fainter and more distant galaxies. The three observatories, Euclid, JWST, and Roman, represent complementary instruments designed to approach the same fundamental questions from different angles, with their combined datasets providing coverage across wavelength, depth, and sky area that no single instrument could achieve. The unexplained images that Euclid captures are not unexplained in the sense of being genuinely mysterious. They are unexplained in the sense that every one of them contains something that was not in the catalog before. A ring that hid for 140 years, a galaxy in a cluster that has never been cataloged, a microlensing event in the galactic bulge that will reveal a planet orbiting a star thousands of light years away. In a survey designed to observe 1.5 billion galaxies over 6 years, new things are not exceptions. They are the point. And the October 2026 cosmology data release, the first full scientific output of the Euclid mission, will be the moment when the universe stops being a collection of unexplained images and begins, piece by piece, to be understood. The single most striking visual in Euclid's catalog, the one that most clearly demonstrates what this observatory is capable of producing that no previous instrument could, is not the Einstein ring or the galactic bulge mosaic. It is the composite image released from Euclid's first science observations in 2023, showing a wide-angle view of the Perseus galaxy cluster. In that image, the foreground cluster and its 1,000 galaxies occupy the bright central region. But surrounding them, in the deep background that Euclid's sensitivity revealed, are approximately 100,000 more galaxies, each one a system of hundreds of billions of stars, many of them billions of light years farther away than Perseus, all captured in sharp detail in a single exposure. Some of those background galaxies show the characteristic arc shapes of gravitational lensing by Perseus cluster dark matter. Some show the irregular, disturbed morphologies of galaxies that have recently undergone mergers or interactions. And some are so faint and so distant that they have never appeared in any previous sky survey. New objects added to the catalog of known structures in the universe simply because Euclid looked at the same patch of sky that previous telescopes had imaged and saw deeper. That is what an unexplained image from Euclid actually contains. Not supernatural phenomena, not anomalies that challenge physics, something more profound, a universe that is larger, more populated, more structured, and more full of things that science has not yet named than any image taken before revealed. Every time Euclid releases a new frame, the count of known galaxies grows. The dark universe that the mission was built to map is not a void, it is a fabric woven with matter, and dark energy. And Euclid is the first instrument precise enough and wide enough to read the full pattern of it. The unexplained images it captures are not unexplained for long. They become data. And data, in the hands of 2,000 scientists across 15 countries, becomes understanding.